Hi everyone, this video is part of Macquarie University's coding tutorials, and today we'll be learning about how we might convert an iterative solution into a recursive one. We'll compare the main differences between iterative and recursive solution design. Then we'll take a look at a sumRange method using a for loop, convert it to use a while loop, then convert it into a recursive solution. It's important to note that this is typically not how recursive solutions are made. This is just another way to show how recursion works and allow you to directly compare the two designs. Before we dive into code, let's take a moment to understand the difference between iterative and recursive designs. An iterative design involves solving a problem by repeatedly performing the same operation until a specific condition is met. This is typically done using loops and for problems where a sequence of linear steps is required to reach a solution. On the other hand, a recursive design involves breaking a problem down into smaller subproblems. We then solve these subproblems by calling the function again with the smaller inputs until a base case is reached. With this in mind, let's move on to our example of converting an iterative solution to a recursive one. To help illustrate the conversion process, we'll be using a sample function called sumRange. The sumRange function takes two arguments, low and high, and returns a sum of all integers between and including low and high. Here we have a version of the sumRange method that uses a for loop. We see it declares a variable called total and initializes it to 0. We then see the for loop is used to iterate through the range of low and high, and during each iteration the current integer is added onto the total. Once the loop is complete, the total value is returned. Now let's transform this into a solution that uses a while loop. A while loop is still an iterative design, but it will make it easier for us when we convert it to a recursive solution. First, we want to change the word for to while. Then we take the int I is equal to low and put it just before the loop. Then we want to take the increment part of the for loop and move it to the very end of the loop. The loop condition stays the same as we want to keep looping for as long as I is less than or equal to the number high. Now let's just quickly run this function in the main method to see how it operates. Let's call this function with the parameters 5 and 10 and print the result to the console. We should expect the result of 5 plus 6 plus 7 plus 8 plus 9 plus 10, which is 45. Now if we run our program, we see we get 45. To turn our iterative solution into a recursive solution, we need to know that we can only pass two values to the next function call as we have two parameters. In order to pass more values or information between function calls, we'll need more parameters, which we'll go over in the next video about tail optimization. Let's start with our base case. This will be the loop condition that we have, but in an if statement and with the condition reversed. In this case, the opposite of low is less than or equal to high is low is greater than high. The reason we reverse this condition is because we are interested in when we should stop making recursive calls. So once low is more than high, we need to stop. Next, we need to think about how our total variable fits into our recursive method. We mentioned that with our two parameters, low and high, we can't pass any extra information between function calls. So how do we keep a total? Well, the short answer is we don't. Instead, we add the low value onto the result of the next function call. Using our analogy, think of this as our manager holding onto the low value that they know of, delegating the rest of the work, and adding low onto whatever result they get back. To write this in code, we need to write return low plus some range of low plus 1 and high. Here we say that I want the rest of the range summed, and once I get the sum back, I'll add my low value onto it. If we were to trace this out, the first function call would return 5 plus some range of 6 and 10. Some range of 6 and 10 should return 6 plus 7 plus 8 plus 9 plus 10, which is 40, and we'll add our 5 onto it to return 45. Notice that when we recursively make the next function call, the value for low is changing while the value for high does not. We need high to remain the same to eventually reach our base case for this problem. And that's it. We've successfully converted the iterative solution to a recursive one. Let's now run our code again, passing in the same values as we did previously, and we get 45, which is the same result as we get with our iterative solution. Just to reinforce the process, let's take a look at a diagram that uses our work delegation analogy. At each step, the worker will ask themselves if low is more than high. If it is, the worker will return 0, and if it isn't, the worker will hold onto its low value and ask the next employee to give back the sum of the new range. Once that next employee comes back with an answer or result, the worker will add its low value onto it and give the resulting total back to the employee who asked them for it. We start with the CEO asking the first manager for some range of 5 and 10. For ease, we'll number our employees. Employee 1 will say, I'll hold on to a 5 and ask employee 2 to find some range of 6 and 10. Employee 2 will say, I'll hold on to a 6 and ask employee 3 to find some range of 7 and 10. Employee 3 holds on to 7 and asks employee 4 to find some range of 8 and 10. This pattern continues to employee 6 holding onto a 10 and asking employee 7 for some range of 11 and 10. Employee 7 then spots that 11 is more than 10, so they give back or return 0. Now the function calls will start to be resolved and the information will flow back towards the CEO. Employee 6 gets the 0 from employee 7. They add their 10 onto it and return the resulting value of 10 to employee 5. Employee 5 receives the 10 and adds 9 onto it, resulting in 19. They then pass the value 19 back. Employee 4 receives 19, adds 8, and passes along 27. Employee 3 receives 27, adds 7, and passes along 34. Employee 2 then adds 6 onto 34 and passes along 40. The first employee now takes the 40 and adds 5 onto it, returning 45 back to the CEO. We can now look at this diagram that shows this same process just visualized in the call stack. The first call is at the bottom and the subsequent calls are stacked on top of it. Feel free to take a minute to pause the video and ensure you understand the process, perhaps even creating another sample function call in main and tracing through the added stack frames on paper. It's important to note that starting with an iterative solution and converting it to a recursive one is not a good approach to solving problems recursively. However, it can be a helpful way to better understand recursion as we can see the similarities between the recursive solution and the more familiar iterative solution. However, we shouldn't see recursion as a substitute for loops. Recursion is a more powerful technique of problem solving, particularly when a problem contains a lot of branching, as we briefly touched on when we looked at the tree structure that occurs when delegating work. We'll see this even more when we look at exhaustive recursion with arrays in an upcoming video. In summary, it's much better to design recursive solutions by using the approach we had with the shopping on a budget problem, where we identified the recursive nature of the problem and thought about what our base case and recursive cases are. In this video, we looked at how to transform an iterative algorithm into a recursive one. We also saw how we can calculate a total without specifically declaring and working on a total variable. This will be useful when we deal with non-numeric algorithms such as reversing an input string. Do remember, this is not the best way to design a recursive algorithm. Instead, you should follow the approach shown in the previous video. In the next video, we'll take a look at what tail-optimized recursion is and make our recursive sumRange method tail-optimized. We'll also see how this changes the process in our work delegation analogy. See you there!